So, hello everyone. So today we are going to have a lectures about Slurm given by Damien Francois. So thanks a lot, Damien. The floor is yours.
Thank you, Olivier. So until now, if you followed the HPC sessions, you've learned how to access the cluster. You've learned how to copy data to and from the cluster. You've learned also how to create parallel software. You've learned how to compile code and use optimized libraries. The thing that you did not learn about yet is how to actually run the software on the cluster. And the short answer is that you need to submit a job to the scheduler. So first, definitions. What is a job? You see here from the dictionary, a job in the context of computing is just an operation or a group of operations treated as a single and distinct unit. So actually you decide what a job is. It could be running one parallel program on multiple data or running a program that produces data and so on. So the first important term is job, and the second one is the scheduler. So this job scheduler, also called the resource manager, is a piece of software which does mainly two things. First, it manages and allocates the resources. So for instance, it knows that there are 2 computers available for a certain amount of time. And it also manages and schedules jobs. So it decides whether your job goes first and then yours and so on. Besides those 2 important things, it does a third thing, which is to set up the environment for distributed computing, as we will see in the future. A few words about resources. So what are resources? Mainly CPU and memory, but there are other types of resources such as disk space and so on. And maybe just a quick reminder, you know that the cluster, they live in racks in a data center. And in those racks here, you see computers, and every item which I highlight here is a computer, and a computer looks like this once you remove it from the rack. And so this is the same computer, and in the computer you have a motherboard on which you have some memory. Here is a space where you put the CPU, and the CPU has multiple cores. Here you see there are 8 cores on the CPU. Some nodes also have GPUs, so accelerators. Maybe you learned about CUDA and directive-based programming 2 days ago in the session. And there is some local storage also in the form of a hard drive. So all those components are managed by the resource manager, and in our case, the resource manager is Slurm. So Slurm is a piece of software which is free and open source. It's quite mature because it exists since approximately 2003. There's a very active community, and there are many success stories. It's also the name of an intergalactic soft drink popularized by the Futurama cartoon. Slurm is highly used in the world. As you can see here, the last HPC user site census in 2019 shows that Slurm is actually the market leader, and previous figures from the top 500 list showed approximately 60% of the top 500 clusters use Slurm. So in this session, you will learn how to create a job, monitor the jobs, control your jobs, and get accounting information for your jobs, all using Slurm. So to create a job, the first thing you need to do is to make up your mind. You need to think about 2 things. First, the resources that you need. For instance, you need 1 CPU core and 2 GB of memory for, let's say, 1 hour. And these are called the job parameters. And you need to decide about the operations you need to perform. If you remember, a job is a set of operations. And for instance, you need to launch a program which you compiled by yourself, and it's named, by example, myprog. And those are called the job steps. So when you are all set with what you need to do, you need to put them in a submission script. So a submission script is a shell script. So here the example that you see on the screen is a bash script. And it's composed of several parts. So here you see the shebang, which says which interpreter to use. It's very classic for bash script to start with bin bash or bin user bin env bash. Then you know that in bash those character denotes comments. And you see here that two types of commands. Here, job parameters, for instance, is a regular bash command, but here this command starts with sbatch. So you see here it starts with sbatch, and this one too. So these actually are commands as seen by bash, but they are interpreted by Slurm as being parameters for the job. And so here you see I have a parameter named job name, and the value is demo. I have another parameter named output, and the value is res.txt. These are other types of parameters which concern the type of resource you are asking for. We will see this in more details a bit later on, but this requires 1 CPU, and this requires 2 GB of memory. And this is the time that your job is supposed to run. So here you have the job parameters, and here you have the operations with here an example of simple bash commands, regular bash commands here. And you see here usage of the srun command, which is not used in Slurm to create a job step. So here I'm creating a job step with this program consuming this data. We'll see a bit later on exactly how srun is used. Most of the time for very simple jobs, you can just ignore srun and just use simple regular bash commands. But if you want to do something more elaborate with the parallel jobs and so on, you will need to use the srun command. Something that is very important is that it's not possible to put a bash variable in here. The reason is that this is part of a command in bash. And so if you put here something that is $ something, bash will not interpret it. It will not expand it. And Slurm does not have the inner workings to do the job to expand variables. So here it will not work if you try to put bash variables. You see here some example of sbatch parameters. Here are some other examples on clusters that are heterogeneous. So on clusters that have different types of hardware, you can use the -- constraint option here to choose a specific type of nodes. You can use the -- gres, which stands for generic resource, to specify that you want to use, for instance, a GPU. On some cluster, also you have licensed software with a limited number of licenses, and you need to request in your job script a certain amount of licenses to be able to start, for instance. You can specify a partition. All the nodes in the cluster are organized in partitions, so the partition are just specific set of nodes. Sometimes they are organized by type of hardware, sometimes they are organized by type of submission policies. It depends on the clusters. You can also have on some cluster QoSs, so quality of service, which are a way to give some user or some jobs some additional permissions. And then there are here the parameters that you can use to specify how many CPUs you want to use, and we will see them in details later on. So maybe I can show you if I'm connecting to a cluster here at UC Louvain called Manbach, and I will show you this one because it has a large number of different type of compute nodes. Here, if I type the sinfo command, which we will see a bit later on, you see that there's a large number of nodes, each with very different type of CPU. You see AMD CPU, you see Intel CPU, and using the -- constraint, you can actually direct your job towards a certain type of CPU. You see also here that we have generic resources in the form of GPUs, and so you can use -- gres to say, okay, I want to run a job with a GPU of type v100, for instance. There are other useful parameters. For instance, you can give your job a name. You will see that when you submit the job, you get by Slurm a job ID, which you can use to manage the job afterwards. But sometimes it's more convenient to choose a name for the job, and then you can use the job name instead of the job ID. You can also attach comments to the job for whatever purpose you might have. Something that is very interesting is that also you can get email warnings. So the thing is that you will submit a job and you don't really know when it will start or when it will stop. So you can get Slurm to send you an email when your job begins, when it ends, when it fails, or also 90% at 90% of its requested time. You just need to specify your email address specifically. You can also set the name of the output files, because your program will start on a computer to which you will not be connected. So everything that the program might want to print on the screen in a regular setting on the cluster, it will save it to a file. And the name of the file is chosen with the -- output parameter. And you see that this -- output parameter accepts placeholders for here, for instance, the %j is the job ID. The same holds for the error. So you have learned about the standard output and standard error in the Linux session. So here you can redirect the standard output to a file and the standard error to another file. If you do not specify this parameter, both will be merged into the standard output. This is a nice small parameter which you can use to actually test your submission script and get an idea of when your job would start if you submitted it right now. Sometimes it's handy to test the actual load of the cluster. It's not always a very accurate prediction, because it depends on the job that fail early, on jobs that are submitted later on. But it's a nice thing to look at. Also, you can specify an ordering in your jobs. If you have multiple jobs and one is performing some pre-initialization and the other is doing post-processing, you can say that the one job needs to start only after some other job has finished. Or you can say only if the job has finished properly, or only if the job has failed. And there are a large number of options which you can choose from to explain the dependencies between the jobs. So when all of this is written in your submission script, what you need to do is actually submit the job. And you do that with the sbatch command. So the sbatch command is the command that you use in Slurm to submit the job. If you've used PBS Pro or SGE in the past, the equivalent is qsub. So the command needs a submission script, and also you can add additional parameters here. So the parameters, you can add them in the submission script. That's the most usual way to do it, because it helps you have keep track of what the parameters you requested. But you can also add some additional parameters on the command line, and we will see later on that this can be handy sometimes. You can also pass some parameters by the environment by setting environment variables. So once you've run this command, you see that it responds with a big number, a large number here, which is the job ID. And we'll see that after you have submitted a job, you can manage your job and refer to it with a job ID, or as I said before, with a job name if you set one. So I suggest that you first try to submit a job to a cluster. So basically, you can connect to any CSC cluster. They are all running Slurm, so it should work on any CSC cluster. You can open a text editor. You can use Vim or Emacs or gedit or Nano, any text editor that is installed on a cluster, and you can write a simple script, for instance, that will run the hostname command, and then you can submit the job, and you can look for files created in your directory. So, for instance, I will go to a CSC cluster, let's say Hercules. in Namur. Okay, I'm connected. So I like to use Vim, so I will start Vim, and I will create a submit.sh. If you remember in the slide before, I need first to set up the interpreter -bin, and then I can put here, for instance, a job name. I want only one CPU, and then, okay, I don't need much less. Something which is important is the time, and I will set it to 10 minutes. So this is, there are many different ways of expressing time limits in Slurm. This is when you use only one column, it's minutes, seconds. You can be more explicit with like this, so 0 hours, 10 minutes, and so on. And then it's not a very complex script, so I will not need to create a job step. So I will just run, use the hostname command. And now I will try to submit it like this with as batch submit. And it says, okay, just like in the slide, submitted batch job. And here you see this is my job ID. And it also specifies on which cluster I have submitted, because Hercules is part of the Slurm Federation. So actually from any cluster in the Slurm Federation, you can submit job to any other cluster. We'll see that a bit later on. And so if I look in my directory, I see that I have a file named Slurm dash, and you see here it's the same number as the number here. It's because this is my job ID, because by default, Slurm will name the output file Slurm dash job ID, but you can change that as we saw. And so if I want to simply see what's the input, I see here the output of the hostname command, which is a command which I put in the submission file. And it tells me that my job has run on the R2W067 compute node. Okay, I hope that you've all been able to submit the file and look for the file that we're creating in your directory. You will have other opportunities to submit jobs anyway. So once you have submitted a job here, you saw that job has run very quickly because it was a very small job and it could be scheduled. It has been scheduled very rapidly, but most of the time when you submit a real job, you will have to wait in the queue. And the queue is the set of all the jobs which are waiting to be scheduled. And to see the contents of the queue, the command that Slurm offers is named SQ. So SQ, it allows you to view information about jobs that are running or pending. There are options to SQ. One very interesting is SQ-start, because it will try to give you an estimation of when your job is supposed to start. SQ also have parameters to specify that you want only to see your jobs. By default, SQ will show you the jobs of every other user. So if I run SQ here, I see a large number of jobs seen by different users. If I just use -u and then DFR, DFR is my login on SESI, I see only the jobs that I have run, but I have none, so the list is empty. SQ also accepts many parameters to decide the columns which you will see. So for instance, here you see that there are 1, 2, 3, 4, 5, 6, 7, 8 columns, but you can actually choose which column to output with this. And those of you who are familiar with the printf-like statements recognize that this is a format string and where a %j refers to some of the column. Okay, so there's a question, how can I estimate how many resources I need? This is a very, very large question. I have a few slides about that a few in a like 10 or 15 minutes they should appear. But I can already tell you that I do not have a definite answer on how to estimate actually which resources, but we will see some hints in a future slide. And then you can use -n to specify that you only want to see the jobs that run on a specific node, and -S to see to use a different sort field, because you can ask Slurm to sort the jobs when you use the SQ command. So you can try to submit another job, and we will do a job that stays a bit longer, so we can see it in the queue. So here I will replace the hostname command with a sleep command, and I put here a large number, and I will say here that I only want 5 minutes. So you see that the time I request is very small compared to the number of seconds here that I expect my job to sleep. But anyway, this will be a longer running job than the previous one. So here again, I can submit it, and I have another job ID. And now I can use SQ-J, for instance, to see the job ID. And you see that my job is pending. And the reason it is pending is priority, and I will have a few slides about priority later on. So I can also use SU DFR, or if you don't want to type your login name explicitly, you can use the $user environment variable, which is set by Slurm by bash when you start. And you see now that in the meantime the state has gone from pending to running, and so we have here the node lists, and we're actually running on the same compute node as before. So here again, we will have a file created in the directory. If I go a bit further, besides SQ, you have sprior, which is a command that gives you the priority of your jobs. So the jobs are organized in the queue by priority, and Slurm tries to reserve the resources for the top priority job. So it's very important to know what the priority of your job is to have an idea of how far from the top it is, and how far away it is from being scheduled and run on the cluster. So sprior has several options also. -L gives you more information. It stands for long. You can also specify the outputs you want, just like with SQ, using the same formatting type strings. And sprior -W will give you the weights. And so what are the weights? Actually, the weights are those which enter the formula of the computation of the priority. So the priority on all the clusters in SESI are computed the same way, though with different weights. So it's all a sum of different, they call it factors. So one is the age factor, is how long your job has been waiting in the queue. The fair share factor is the most important one. It's a measure of how much you've used a cluster in the past. So the idea is that people who have used a cluster a lot in the past have less priority than those who did not use a cluster at all, for instance. The job size can also be a factor, specifically on clusters that have a very fast network. We tend to favor very large jobs, which otherwise are very difficult to schedule, so they get a higher priority to compensate from the fact that it's much more difficult to find a large number of CPUs available at the same time. And then you can also have a partition factor, so depending on which partition you submit your job, the priority could be different, and also a QoS factor, quality of service. So typically the quality of service is used to give some jobs a priority boost, typically on hardware that has been paid for by a specific group. They get a QoS to access that specific computers with a higher priority. And then the last element, the last term in the sum is another sum, which is a combination of the resources that your job requests. So one of the resources is the number of CPU. So this is actually redundant with this factor, but actually you can have here many other types such as memory or bandwidth or disk that can enter the computation of a priority. But most of the time on the CC cluster, we do not use those. So here you see the output of SW prio, S prio -W on HMAM, which is the whole cluster that was decommissioned this year. And you see here the weights. Okay, I can run the same command here on Hercules, and you see that the important factors here are the age, fair share, and the job size. So you can try to connect to a cluster just like I did and run the S prio -W to see what the priorities are. And if you want to have a look at exactly how the Slurm is configured on that cluster, you can use the scontrol show config command. It will dump the whole configuration of the cluster, and you can use grep to see anything that is related to priority. And you see here priority parameters, there are none, but you see the weights here, the same weights that were given you as the output of the S prio command. You see here max age, which is a time after which the job aging does not give additional priority at all. You have here also the decay half-life, because I said that the fair share is a measure of how much you've used the cluster in the past, and actually there's a half-life decay applied to that measurement, so that actually if you use the cluster for 1 day, if you use a full node for 1 day a year ago, it has nearly no impact at all on your priority, while if you've used a full node for 1 day ago, it has a high impact on your priority, but we will see that again. So one very important thing in the scheduling is the priority, but another important thing is the backfill. So I need to explain a bit backfill here. It's a rule that says that a job with a lower priority than the top job can start before that top job, if and only if it does not delay the starting time of that priority job. So small illustration here. This axis is the time, this axis is the resources, and the job is a request for resources over some time. So we can depict it with a square, and you see here 1 job, 2 job, and a 3rd job. And this number here, we will say that it's a priority. So this job has priority 100, this one 70, this one 80. And so we are assuming that we are already running at some point, so we have those jobs running or being scheduled. Then we have 2 jobs that appear. Okay, and this one is a large one. You see it requests large amount of resources, and the priority is 90. And this one has a priority 10, and it requests less resources. So Slurm will first organize resources for the large one, so it will schedule the last one. But then you see that you have here some space where you can actually fit that other job. And this job, although it has a smaller priority, it will start before this other one, because anyway, this one cannot start until this job is finished. So this process is called the backfill, and it's very important for you to know about backfill, because depending on the time you request, your job could start very soon or not. If you have a small job that you know will take only a few minutes, it's very important that you specify that your job will run with the -- time option only for a few minutes. Otherwise, if you release the default or the maximum hold time, which is maybe 5 days on some clusters or even 15 days on some others, your job will not be backfilled by the scheduler. So once your job is submitted, you can control it in some ways. One very important option is to be able to cancel a job. If you submitted a job and you just realize that it's not going to do what you wanted to do, or you made a mistake at some point and you want to cancel it, or it's not converging, maybe you want to cancel it, you can use the scancel as your guest command. Also, the scancel has options which you can use to specify the jobs. By default, you give it the job ID, so you can use scancel and then your job ID. By the way, it's maybe time to see if I still have here jobs. I don't have any more jobs. So if I look at the files, I see that I have a second output file, and if I open it, you see that actually there is an error here that says that my job was cancelled due to time limit. Because if you remember, I set the time limit of 5 minutes and I had it sleep for several thousand seconds, so it could not match. And if you try to overuse the limits, Slurm will cancel your job. So here, I didn't specify job name, but if you specify job name, you can cancel by giving the job name. You can also scancel -u mylogin to cancel all jobs that you have submitted. Of course, you cannot cancel jobs from other users. You can try, but it will fail. You can also specify that you want, for instance, to cancel all the pending jobs or all the running jobs with the -t option. And then scancel is a bit like the kill command in Bash and Linux. You can use it to send specific signals, unique signals to your job. And you will see that it's very handy in the session that is given this afternoon by Olivier. You can cancel your job, but you can also modify it with the scontrol command. Basically, scontrol is the command that is used mainly by the system administrators to manage the backend aspects of Slurm. But users can use it to update their jobs. So you can use scontrol update, and then you give the job ID, and you need to you give the parameter which you want to modify. So for instance, here you see that on the first line, I want to modify the partition. Maybe I submitted a job to the main partition, and I want it to run in the debug partition. I can use a command line like this to reroute my job for the main partition to the debug partition. Also, if I realize that I have asked too little time or too much memory, I can also modify them. For instance, here you see on the second line, I am requesting 1 day. So 1 dash something refers to 1 day. And then I specify the memory again. Most of the time, you will only be able to modify jobs that are pending. Once a job is running, you cannot modify most of the options. One thing which you can modify on a running job is the number of nodes. You can reduce it. Of course, you cannot increase it, but you can reduce and release nodes which you are not using if you need to. Another command which you can use is SView. It gives you a visual overview of the cluster, of your job, of the partitions. And rather than running command line commands, you can run the SView software. It might not be installed on all clusters, and sometimes there are options which are not available through SView. Personally, I don't use it much, but if you prefer to click, you need to know that it exists. So once your job has been submitted, maybe cancelled, resubmitted, and you have a large number of jobs, you can have an accounting. So a list of the jobs which you have submitted, and the command in Slurm to get access to that accounting is called sect. So just like sq, sect can work given a job ID or job name. You can choose the columns, and actually here sect was not designed to use format strings with the % something, but rather the full column names. So here it's a bit more easier to understand with sect -o here, user, total CPU, and so on. You can specify the names of the column, so you don't need to remember the specific % sign related to the columns you want to see. Actually, the SQ, sinfo, and so on commands have also been enhanced with that type of column choosing options. So with SQ, I show that you can use -O and then % something, but you can also use -O and then the column names. So we can try to run it here. So if I run sact like this, I see that I have submitted 2 jobs today. By default, sact will give you the jobs that you have submitted the same day, but you can use start equals and then maybe something like this to give. Oops. Okay, I didn't submit a job for a long time on that cluster. So, but anyway, you can choose the starting time and the ending time also of the period you want to get an accounting for your jobs. And you can say here the column by default, which is the job ID, the job name, the partition, the account, because actually on the CC cluster, we are all part of the CC account, but on some other clusters, there can be different accounts depending on who has funded which part of the cluster. The number of CPU I requested was always 1, and you see here the state. So here the first one was completed, and the second one was cancelled due to timeout. And you see, actually I have 1 line here per job, and this is a summary of the job. And here you have a second line, which is specific to the bash script. So when you will have more job steps, you will have more lines here. And when you don't use srun, so you don't create any job steps, there's only 1 job step, and it's the one related to the submission script itself. So if you run sact on a cluster, you should see the list of the jobs which you submitted right away on the same day. Sreport is another command aimed at requesting information from the accounting, but this gives you more information about the total amount of resources you've used, so aggregated over all jobs that you submit. So it's a query language similar to MySQL, to a SQL actually, but you use Sreport cluster and then some keyword user utilization by account, for instance, but there are other keywords. Most of the time, you will not have to look into this unless you need to report to authorities or funding authorities how much you've used the cluster in the past. Final comment in Slurm about the accounting is the S-share. So S-share is a tool for listing the shares of the Slurm calls that association. So on the cluster, an association is a tuple made of a username, account, partition, QoS, and cluster, and so on. So basically, you need to think of an association as your account. And if you use the S-share command, you see here that there are typical columns, and one here is the account. So you see that they are actually this was run on the method 3. So if you want to have the same output, you should run that command on the method 3. So you can see it here actually. So there are 2 top accounts. One is root and the other one is CC. And you see here the row shares, which is the part of the total amount of computing power delivered that can be delivered by the cluster and how much it is distributed in the different accounts. So you see the CC account as a very large number and the root account as a very small number. It's only 1. And here the soft user is the one that is used to actually build the software on a cluster. So we submit job sometimes to build the software, and that user needs to have some access to the nodes as well. And then here you see that everyone has the same share, it's 1, and the share are then normalized as 1 over the total amount of users. So there are approximately 3,000 users defined on the CC database. So you see that everyone is entitled to this fraction of the total amount of CPU hours that the cluster is able to deliver over a given period. And then you see here the row usage, which is the number of CPU seconds or minutes, I don't remember, that you've used in the past. Here the column is a technical one. Actually, it's not important in the SESI context because we have no hierarchy other than root and SESI. But on some other clusters, you have a very complex hierarchy of accounts, and each account needs to have access to a proper share of the cluster, and this effective usage is actually the usage that is accounted on you, but based on the jobs of these other users that are part of the same account. So here, as everyone is part of the same account, it does not change anything. And then here you have the fair share. So I said a few words about the fair share. In the past, it's a part of the computation of the priority. And you see here, basically, that the fair share is a value which is close to 1, like here, if the usage in the past is close to 0. And if we look at a user that has used the cluster a lot here, you see that the fair share is closer to 0. So fair share is a very important concept in the computation of the priority, so I will spend a few slides explaining it a bit. So fair share directly influences the job priority, as I said. A share is allocated to you, which is 1 over the number of users. And as I show you, if your actual usage is above your share, then your fair share value will be shrunk to 0. But if your actual usage is lower than what you are entitled to, your fair share value is increased towards 1. And this 0 to 1 range is multiplied by the weight we've seen in a previous slide. One important thing is also that the actual usage taken into account decreases over time with a half-life decay, as I said earlier. So if you used the cluster a lot 2 days ago, it has a higher impact than if you use the cluster a lot 2 years ago. If you look in the Slurm documentation, you will see that they offer a simplified formulas, but basically you see it's a negative exponential that takes into account the usage of the cluster and your share of the cluster. Maybe I can explain it a bit better with an example. So here, assume that I have a cluster, I have 3 users, and I have a 3-core or 3-node cluster. And in the same time of graph as before, you see here that we have the size of the cluster. So we have node 1 here, node 2 here, node 3 here, let's say. And here you have time. And you have 3 users, which I assign colors to. So user blue, green, and red or orange. I would say red. So you see that user red uses only 1 core for the total amount of the period, and user blue uses twice the same amount of cores, so 2 cores for half of the period. And then after this point in time, it does not use a cluster anymore, and there's another job by user green that has the same size. Now, in terms of cumulative usage, what does it look like? So you can understand that green has a 0 usage until it starts its job, and then the usage of blue does not evolve anymore as soon as the job stops. So this point in time is exactly this point in time. Red is using 1/3 of the cluster, and there are 3 users, so it's using exactly its share. So the slope of the increase here is exactly 1. Here, blue uses twice its share, so the slope here is 2, and the slope is the same here because the job size for both users is the same. So I said that there's a decay. So actually, Slurm is not more interested. Is not more interested in those figures than actually in those figures. And you see that here there's a slight curvature, and then here, as soon as blue stops using the cluster, you see that the cumulative usage decays. Okay, so these are the actual figures that Slurm uses to estimate the past usage of the cluster. So I come back from this slide. So you see the usage of the cluster decaying when it's not using the cluster, and this relates directly to the fair share. So red has been using its share of the cluster, so actually its fair share is exactly a half. By contrast, green has not been using the cluster until this point in time, and so here you see it has a value of 1. Blue, has been using twice its share, so actually the fair share value is a quarter, so 0.25. And then when we are here, you see that things do not change for red, as it's still using its exact part of the share of the cluster, but then the fair share drops for green because his job has started, and the fair share increases for blue because his job has stopped. If you want more information about that, you can have a look on the Slurm documentation or on the CC documentation. There's a page on the CC documentation that gives you all the pointer in the Slurm documentation, which has a large amount of details about how priority and how fair share is computed. Okay, I don't see any more questions published, so I will just keep going, but do not hesitate to ask questions on the chat. Until now, you've seen how to submit jobs and get information about your jobs, but it's also important to get information about the clusters by themselves. And the command that you can use is called sinfo. If I go back here, if I use sinfo, I'm asking Slurm, okay, what does the cluster look like? And here on Hercules, you see that sinfo has some partitions. The cluster has some partitions here. Batch, HMEM, and CBS, and this. And those are, for instance, this is a partition for nodes that have a large amount of memory. This is a partition for nodes that are aimed at visualization. And you see here the list and the states of all the nodes. There are other options you can use in sinfo. By default, it will give you the output organized by partition, but you can ask for the output organized by nodes with the -N-L, and you then have a row on the output by compute node, and you see in which partition they are, their state, how much CPUs they have, how they're organized. So for instance here, this says there are 2 sockets. So I will show it. So there are 2 sockets, 8 CPUs per socket, and 1 thread per CPU. So socket, cores, and threads. And see here you see the reason why a node is down, and it can be because it's not working anymore, or it has some issues that needs to be solved. And you can also, as the last example here, use -R to see the list of nodes which are down on the cluster. Okay, and it works exactly the same on the other clusters. So if I go here to Lemaitre 3, sinfo, you see the same thing. Here you see only 2 partitions, batch and debug. And you see if I run the same command, then that we have 1 node which is not responding, and you see here the available feature. So here the column is a bit too small to actually see that we have 2 types. Oh no, we can see it. So we have 2 types of CPUs on Lemaitre 2, on Lemaitre 3, the Skylake and the as well. So the as well are all part of the debug partition. So something you need to think about, into account on Lemaitre 3, which is a mostly homogeneous cluster, mostly the same compute nodes, but we have 4 nodes which are different from the others. So you can try, sorry, you can try this sinfo command, and you can use the -- clusters command here. So here, if I want information about Hercules, I can request it. Okay. 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 So did I make? Okay. I don't know exactly. Maybe I need to put it here. No. But here, anyway, you saw that I'm connected to the method 3, and I can get information about Dragon 2, which is another CC cluster set. And sorry, it was Hercules 2. So if I run sinfo -- cluster Hercules 2, then I get information about Hercules 2, and I can get information about all the clusters that are part of the federation. So Dragon 2, Hercules 2, and the method 3. And the same holds with the sact command. You can use the federation option to get the information about all your jobs in the federation. So those 3 clusters are part of the same federation. We are hoping to incorporate the future NIC5 also in the federation, but that will be a bit later on because there are technical issues that we need to take care of. So until now, we have seen how to submit jobs in a batch way. So you submit a job and then you do something else, and you come to see the result of the output later on. If you have a job that needs to be interactive, so if you need to submit a job and then be able to interact with the job, you need to use either the salloc command, but this one is a bit more complicated to use, and most of the time it's not necessary to use it, and you can use directly the srun command. If you use srun --pty bash, actually Slurm will submit a job and give you an interactive bash process on a compute node. And srun accepts exactly, nearly exactly the same set of parameters as batch. So if you want to have specify the amount of memory or the running time or the number of CPUs you need, you can do it with srun. So I can maybe try it here. So I will show you on the debug partition. So debug, and then pty bash. It says that the job is queued and is waiting for resources, and then it says, okay, I've been allocated the resources. And here my prompt is a bit misleading, because if I run the host name, I'm actually on the 94 compute node. So if I go to Hercules again, I can run the same command, pty bash, and here, well, I is waiting for resources. So I will come back to it later. You see that here, if your job is not, if Slurm is not able to schedule your job immediately, you need to wait. And at some point, when the resources you have requested are available, you will get interactive shell on compute node. Okay. So a little summary. You know how to explore the environment with the sinfo command with --node --long, which is equivalent to -N lowercase l. And you can get node usage by using sinfo --summarize. So if you want to see how much jobs or how loaded the cluster is, you can use sinfo --summarize. So here, maybe I can cancel this. It looks like I'm not going to have an interactive shell right now, so I will cancel my job. And if I use sact, I'll see that I have a job here which is cancelled. No, it's the other one. So this one is not entered the accounting yet. But if I use sinfo summarize, I see the number of so here you see under each partitions the number of CPUs, or number of nodes, sorry, here number of allocated nodes, number of idle nodes, number of nodes which are in a error state or other. The O here stands for other. And then here the T is the total amount of CPUs, of nodes. So S info dash dash S summarize gives you an overview of how much nodes are available or idle or allocated and so on. And so remember that to submit a job, you need to define the resources you need and the operations you need to perform, and you put them all in a job script. You submit the job script with sbatch, and you can view the job status with sq and get information about past job with sact. And if you want to get an interactive shell, you use slurm dash dash pty and then bash. Or if you want to use another shell, you can use another shell and bash. So now I'm coming back to the question about how to estimate the resources that you need. Okay, so the question in the chat here, I just answered, you can use slurm with another shell, provided that the shell is installed on a cluster. So if you, for instance, you're using ZSH, I'm not sure it's installed on all the cluster, you can always ask, or you can install it by yourself in the cluster. The default shell will always be bash, so when you connect, it will always be bash, unless you specify in your bash.rc that you want to replace a bash with ZSH, for instance, and then you use the exec bash command to start ZSH rather than bash. So back to the resources, how to estimate and choose the number of CPUs, the memory, and the time, and the other items. So actually, it's not an easy answer. And from the user's point of view, what you want to minimize is the time to solution. And the time to solution is two parts: the time it takes for your job to run, and the time your job has to wait in the queue. So here, this would depict the time your job has to wait in the queue, and here the time your job runs. The time that your job will take depends on the number of CPUs you put to it. The more CPUs you put, you can expect that at some point the performance will be better, but remind that if you have attended the parallel computing or the parallel programming sessions, it's not always easy to get faster jobs if you add more CPUs, but most of the time, if you double the amount of CPU, you can hope to have a decrease in the running time. And the time that your job is waiting in the queue depends on basically the resources that you request. So the more resources you need, the more time you will have to wait until these resources are available. And if you need those resources for a large amount of time, you've seen that you will have to wait on average longer time than if you need only a small amount of time, especially due to the fact that the backfill will be able to start your job soon and fill in the holes in the scheduling matrix if the job length is not too large. So if you have a look at the running time, as I said, it mostly is a decreasing function of the size of the job, while the waiting time is mostly an increasing function of the size of the job. So what you need to find in your sweet spot in here. And it's not easy to find, and the more jobs you will submit and the more information you will look about those jobs in the accounting, the more you will be able to actually precisely define how much resources you would need to request. Slurm has two options which you can use in terms of nodes and time. So if you do not know exactly how many nodes you will need, you can specify a range, and Slurm will start as soon as it has sufficiently enough compute nodes available to submit the jobs. It will start. So if at some point you submit a job with 2 to 4 nodes, for instance, if Slurm is able to schedule your job right away with only 2 nodes, it will do it. But if there are 4 nodes available at the same time for your job, it will rather allocate 4 nodes to your job. And then you have a time min, which is the minimum time that you want to request. If you are using dash dash time, Slurm will allow you will allocate to your job resources for that amount of time. But if you use dash dash time dash min in addition to dash dash time, Slurm will start your job even if it does not have the whole time period available, but only a smaller one, but not if that smaller period is smaller than the time min that you specify. So with those 2 degrees of liberty of freedom, you can try to have the backfill kick in sooner. So here is an example. Back to the drawing of the scheduling. Here you see that if you have a job and you use dash dash time min here and dash dash node with a range here, actually your job looks like something which some degrees of freedom, and Slurm can squeeze it into the space allocated here. So if you only specified 24 nodes, for instance, so let's say it's this value, you see that it was not schedulable at all. But if you give Slurm some liberty and you say, okay, with 16, I can handle it, and then I will stop my job and restart later if I need, then you see that it can fit in the square here. So back to the actual question of how to decide how many CPUs, how much memory, how much time. What thing you can do is run a size down program on your laptop. Maybe the first few iterations of your program and so on, and look at the top command in Linux. So the top command will give you information about running programs and gives you the amount of memory that they are using. So it's the res command here, is the res column here. Sorry, and it gives you the number of times the job has been running, and you see here the number of, or the percentage of the CPU it has been using. So with this information, you can have an idea of how much it could take on a larger cluster by using more cores. It's a very rough number, but it's the one that you can actually at least use. Another approach is pragmatically to use guesstimates for the first job, or use very large values. The thing, of course, if you request too little resources, your job will be killed. We've seen earlier that if you request too small an amount of time, your job will be killed, and you will have a message about time limit. The same holds for the memory. If you request not enough memory at some point, and your job tries to use more memory, Slurm will kill it. So what you can do is submit a job with large values and then analyze the accounting information with the exact. And you see here I show the exact command, and I specify the column job ID max RSS, which is a the maximum resident set size in the memory. So this is basically the amount of memory that your job has been using, and it's a maximum over all tasks. And then you have the min CPU that you can use to have an idea of how long it has been running. And then if you have several jobs of the same type that you need to submit, you can extrapolate for other jobs and try to be a more restrictive and more conservative in your, less conservative and more tight in your requests for the jobs. But the best approach is still to use profiling tools. So you can use Valgrind or vTune, the tools that Bernard has presented in the previous sessions, to actually analyze specifically how the memory and how the performance is evolving as a number of CPUs are added. And so you can get get tighter information about the memory usage and the number of CPUs that you will need and the time that your job will need. And then you can use the knowledge that you gain from those tools to actually submit jobs on the clusters and with precise requests. And the more precise your requests are, the sooner your job will be able to be scheduled by Slurm. because if you still request the largest amount of memory and the largest amount of time, Slurm will have to wait until that sufficiently enough nodes are available to cope with your memory requirements, for instance. So unfortunately, I don't have a specific methodology to estimate exactly how to choose the amount of memory that you need and the amount of CPUs and so on. But I give you hints here, either using your laptop on a size down version and using the top command to see how much memory it's using and so on, or submitting a job and then tuning the requests as by having a look at the accounting, or using upfront profiling tools and memory profiling tools to see how much memory and how much CPU your job will need. So if I look at the question, I see that Ariel has also given additional information about using ZSH on the cluster. I think I will have a small break here. This whole first part was about Slurm and how to submit a job and how to manage the job, and there will be a second part of the session about actually submitting and creating parallel jobs, because all the examples I've shown here has been serial job with only one CPU requested, but of course the power of the cluster lies in the large amount of CPUs that you can request for one job. And so there are different distinct ways to request the CPUs depending on the fact that your job is message passing or shared memory and so on. And so the second part will explain all this, and I suggest that we resume at 11 o'clock. During the break, so we will restart. During the break, there is a question, actually 3 questions in one. First question is, should I submit a job in $global scratch or $local scratch, or just in $home? If I submit in $scratch in a node, will it be running only in this node? So the global scratch is indeed a space that is seen by all nodes in the cluster. Local scratch is only local to the node, so you cannot access the local scratch from one node to the local scratch of one node from another node. There's also a local scratch on the login node, but it's also distinct from all the other local scratch. If you want to know more about that, there's a session specifically dedicated to how to manage all those different type of space next week, I believe, by Ariel. So Ariel, maybe you can specify in the chat which day your session is on. And then the third question was, what do you mean by interactive work with srun-pty bash? So the difference was, if you remember, when I run the sbatch command, the sbatch terminates very soon, and then you have your job that is running on a cluster node. Sometimes it's not what you want. What you want is to have directly access to the cluster node, and you use srun-pty bash for that. And then you have seen that srun actually waits for the node to become available, and then as soon as the node is available, you get access to the nodes. So I will try here. You see, it's blocking, so I cannot run any more commands until the job has started. And as soon as the job has started, I will have here the possibility to type my commands, and the command will run in the job on the compute node. So it's interactive in the sense that you have to wait for the job to start, but then you can interact with the compute node on which your job has been scheduled. And then it's different from batch, which is non-interactive, where you submit a job and the job runs on a piece of on a part of the cluster where you cannot have access to, and you only have access to the output through the output files. So here Hercules is quite loaded, so I don't have access right now, and you see that I have to wait because I want an interactive session. Most of the time you want interactive sessions to run some quick tests to make sure that your program can be compiled, for instance, on the type of architecture that you are targeting, or if you need to run some visualization software, you will need to have an interactive session. Also, you can start interactive session to have, for instance, Jupyter notebooks running on a compute node and then interacting with your Jupyter notebook through the network from your laptop to the compute node on the cluster. Okay, so next Wednesday, the 18th, there's a session about how to use a different type of storage that are available on the CC clusters. So back to Slurm. The second part will be about how to create parallel software and how to request distributed resource. I will discuss 6 typical use cases and give some example of submit script for those typical use cases. One is MPI, multi-threaded, so OpenMP, for instance, master-slave, embarrassingly parallel, heterogeneous jobs, and accelerators, so GPUs, for instance. So first with the MPI, so if you don't know what MPI is, maybe you don't need it, but otherwise there was a session about MPI given by Orient Louan a few days ago. So basically MPI is a library that allows you to create parallel software on multiple machines. And so if you have an MPI program and you need to request n CPUs, you need to launch n MPI processes. You do that with the --n tasks option. And so if you need n CPUs or n MPI processes, you ask for n tasks equals n. And then you can use srun or MPI run depending on the version of the library or the type of library. Most of the time now you will use srun, so it would create a job step. And srun will start the myprog utility on all the nodes that were allocated to your jobs, and actually on all the single CPUs that were allocated to your job. And then the OpenMPI library will create the environment and so on. So typically, the minimalist submission script looks like this. So you have the shebang, you have the request for the number of tasks, maybe some OpenMPI module that you need to load if you want to choose the OpenMPI version or the flavor of MPI. And then you run srun myprog. So if myprog is a correctly compiled MPI program, myprog will be run 8 times on all the CPUs that were allocated for your job. So here it's an example where you don't specify too much constraint. You just need 8 CPUs, for instance, and you request 8 CPUs. But sometimes you want 8 CPUs spread across distinct nodes, for instance. For some I/O intensive operations, it can be beneficial to actually have multiple disks on which you can write in parallel and so on, so if you are using local scratch. And so you can do that in basically 2 ways. Always ask for the number of processes that you want, and then you can specify either the total amount of nodes or the total amount of tasks per node. And so if you want n CPUs spread across n compute nodes, you can either request n tasks equals n and nodes equal n's as well, or n tasks equals n and n tasks per node equals 1. On the other side of spectrum, if you want all your CPUs on the same node for any reason, you can use always n tasks, and then n tasks per node is set to the same amount as here, or you can use this way, which is equivalent to this way, but the other one wrong. So with n tasks, n nodes, n tasks per node, you can choose exactly how your tasks or your MPI processes are organized onto different nodes, and you can use the in-between situation, for instance, by specifying that you want 2 tasks per node. Maybe if the node is a 2 socket, you want 1 task per socket, you can specify something like this. You can also use the -- exclusive option here, which is a way to test Slurm that actually you don't want to share the nodes with other users. So by default, on all the CC clusters, the nodes are shared among jobs. So you can request an individual number of CPUs, but sometimes for stability reasons or for performance reasons, you want only your job to be allocated to the nodes that are dedicated to your job. So you use the -- exclusive. Beware that when you do that, of course, you are actually requesting more, possibly more resources than what you expressed with task and memory and so on. And so your job will be scheduled possibly later than if you would not use the -- exclusive option. So with MPI, quite easy. You use srun, you specify number of tasks. It will be mapped to the number of processes in your MPI program. And then if you want, you can specify how the processes need to be spread across the nodes with -- and task per node, for instance. You can specify the 3 of tasks nodes and tasks per node, but it's better to at least have them consistent if you specify like that. So second use case is multi-threading. So here we're not talking about an MPI program, but most typically an OpenMP program or a pthreads program, TBB, thread building blocks program, or if you are using a parallel library like OpenBLAS, or if you are using a Python multiprocessing module, then you are in this framework. So the main difference with the previous is that here you cannot use multiple nodes at the same time. So if you have an OpenMP program, it cannot use multiple nodes at the same time. So here you will always ask for only one task, and what you will request is the number of CPUs per task. So if you want to use n CPU to start n OpenMP threads, then you can use -- CPUs per task equal n. And then you can use the Slurm CPUs per task variable to set the Slurm CPU per task variable to set the value of the OMP num threads or the MK num threads. On some clusters, it's done for you automatically because the administrators has injected that into the prologue of the jobs. Sometimes you need to do it by yourself, so maybe it's better always to specify it explicitly. And here, so you don't need to put here exact number. You can ask Slurm what you have requested, so you don't need to change that when you request more or less cores. And then you can run myprog. The srun here will create one process only, and that process will have multiple cores available to start spawning threads on the multiple cores. So a minimal submission script looks like this. You specify -- CPUs per task equal, for instance, 8, and then you export OMP num threads equals Slurm CPUs per task, and then you run your program. And if your program is a properly compiled OpenMP program, it will be able to use 8 CPUs on the same node. Sometimes you do not want to specify exactly the number of CPUs, but you want a whole node for you. You can use the -- exclusive, as I've explained earlier, but in that case, you can also use -- mem equals 0, because otherwise, if you don't specify the memory, your job might be killed if you use too much memory. If you specify -- mem equals 0, what you are telling Slurm to do is to allocate all the memory of the node to your job and do not kill the job because of memory usage. So if you are only interested in using a full node and your program is able to detect how much memory it has and how much CPUs the node has, you can run it like this with -- exclusive and then -- mem equals 0. So this was for OpenMP multi-threaded in general. You can sometimes have programs which are dubbed master and slave, so where you have one program that distributes work to other programs, which are called sometimes slaves or followers or other terminology. Here you will also use the -- and tasks depending on the number of processes or threads you want to run. The same applies for ntask and CPU per task as for OpenMP and MPI. So if your master slave is able to run on multiple nodes, then you can use multiple ntasks. Otherwise, you can use only one ntask and multiple CPUs per task. And here, if you have different types of programs, so master and slave, you can use the -- multiprog option of srun. So here you will have to start a job step with srun and then -- multiprog and a configuration file, which has to look like this. So it associates the task ID, so it's the equivalent of the rank in MPI or the equivalent of the thread number in OpenMP. And what this says is, okay, you request 8 tasks, and the first one will start the master, and tasks 1 to 7 will start the slave. And then if your program is correctly built, then the master can interact with the slaves to distribute the work. This is mostly seen when you have MATLAB code which you have compiled for the cluster and you want to run it with the multi-core option. This is the kind of construct in Slurm that you will be using. But most of the time, OpenMP and MPI are single program multiple data, SPMD, so you have only one type of program. If you have different types of program, it could be a master slave, or it could be a leader follower, or any other terminology, then you will use a multi-conf to start all the programs that are needed. If you have a program that simply needs to run a large number of times, so you could think you need to submit a large number of jobs, you can actually pack them in what is called a Slurm job array. So to do that, you use a -- array and you specify a indices. So here in the example, I use 1 to n. So what will happen is that actually, even though I will submit only one job, Slurm will create n jobs, and each job will have a Slurm task ID array set to a different value from 1 to n. So what you can use in your submission script is something like that. So sbatch 1 -- array equals 1 to 8, and then use srun your program, and then you can pass the Slurm task array ID to your program. So for instance, if you need to run a program with parameter 1, then parameter 2, and parameter 3, and to 8, you do it like this, and then Slurm will submit an array. The nice thing about arrays is that you can manage the whole array at once. So if you need to cancel the array, you can use the task array, you can use the array ID, which is the ID of the first job, and you can cancel the whole array, so all the jobs. But you can also cancel individual jobs in the array, and so on. So arrays are a nice way to organize a large number of jobs which basically do the same thing, except for one thing or another. For instance, here, if you have distinct files that you need to process, for instance, assuming there are 8 files in some directory, data directory, you can, in Bash, create a construct like this, where you create a Bash array with all the files that you need to process, and then you can run srun your program, and then the files array from which you extract the element which corresponds to the Slurm task array ID. So here, if you have 8 files at this location and you submit that submission files, you will create a job array of 8 jobs, and each job will run the myproc program on one of the files in the directory. Use case 5 is about heterogeneous jobs. So when you have requests which are not homogeneous over all the CPUs. For some programs, it might make sense to request, for instance, as I write here, 1 CPU with 4 GB of memory plus 10 CPUs with 1 GB of memory, or 10 nodes plus one node with a GPU, depending on the type of jobs you have. So Slurm in the latest versions has this notion of packed job, where you can actually have multiple S-batch lines separated by an S-batch packed job and then another line here. And so this will request 4 tasks with 1 CPU per task and 1 GB per CPU, and 1 task with 4 CPUs per task and 16 GB per CPU. And then here is an example of what you can do and check that it has been organized like this. With srun, you can direct your program to a specific, what they call a pack group. So this is one pack group and this is the other. I will not show more examples because most of the versions that are running currently on the cluster has a very limited implementation of that type of job. But basically, if you run it on a cluster that has a sufficiently up-to-date Slurm version, you can start a job with 2 tasks, 2 sets of tasks with different resources, and then you can even cancel a set of tasks and release the type of one of the types of the tasks. Now a few words if you want to use accelerators. So I mentioned accelerators a bit in the previous slides. The way to do this differs on the Slurm version. GPUs are considered in the Slurm terminology GRES, so generic resources. If you have Gen5 or FPGAs, they are all types of generic resources. And so on a Slurm cluster, if you request -res GRES equals GPUs colon some number, then you will request n GPUs. The more recent version of Slurms, for instance, from 19.05, allow you to directly write something like this: --GPUs equals n. So it's a shortcut to --GRES equals GPUs colon n. So if you want 1 GPU, we can just even simply specify --GPUs. Slurm also allows you to specify the type of GPU you want on a cluster. Well, if you have access to a cluster with different types of GPU and the administrators have tagged a type on each GPU, you can specify a GPU that you need. So maybe I can show an example. I will connect to the Manpack cluster here at UC Louvain, because if you look at sinfo, you see that we have Tesla's M10 and V100 and so on. And you see they are in the GPU partition. So what I can do is srun, and then for instance GRES equals GPU 1, and then let's say I will run the hostname command. So this is a way to start an interactive job, but without the PTY. I don't need to interact with it. I would just run a small hostname command, and I need to specify the partition GPU. There are not many nodes in there, so I hope there's one available. It seems not. But here you see I don't specify the type of GPU. So I can specify here with Tesla V100, for instance. You see this is the tag associated to some of the GPUs. I put okay, and so here again, Slurm will try to run my small hostname job on this node or this node, but not on this node. And you see that they are okay. It's starting. So you see that it has allocated to me CAS 101. So you can request multiple GPUs, and on most clusters, if you request a GPU, the environment will be set so that the program, if it's compiled with CUDA, for instance, will know which GPU it can use. And actually, on Manback, for instance, if you request one GPU, and you start the NVIDIA SMI command to see the list of GPUs, you will see only one GPU, even though there are two GPUs on the node, but only one of them will be available to your job. And if you request two GPUs by putting a 2 here, then you will see that you have two GPUs available for your job. So one important thing also is when you request resources for a GPU, even if you need a GPU, make sure to request a certain amount of CPUs for the other parts of the job. If you know exactly how much GPUs you need, then you can request GPUs. Do not ask only one CPU, because most of the time the runtimes of the GPU and the environment around that manages the distribution of the task on the GPU and on the CPU will use as many cores as are available. So sometimes you can think that a job is very slow simply because you only request one CPU. Just make sure to request the correct amount of CPU. And 8, if you don't know, should be something reasonable. Okay, I've seen 6 use cases, and actually you can mix them. So you can have hybrid jobs. For instance, MPI and OpenMP. And if you need to run a job which is both MPI aware and OpenMP aware, you just simply need to collect all the parameters specific to each type. So here I have the parameter specifics for MPI, and here the parameter specific for OpenMP. And so this will request 8 times 4 CPUs, all grouped by 4. So we will have 8 processes created by Slurm, and each process will have access to 4 CPUs on which they will be able to start 4 threads, 4 OpenMP threads, for instance. So if you have a node with 32 CPUs, maybe this kind of allocation will be set on one single node, but if you have only 16, for instance, it will be split on 2 nodes, but always by group of 4s, so that every MPI process will be able to access 4 CPUs to start the threads. And you can start a job array of hybrid jobs if you just simply add the job array here. So you can combine all the elements we've seen. There are specific use cases, but you can combine the use cases simply by collecting all the parameters specific to your use case and putting them all together. Now, a few words about submission. I've said that if you have a few or even a large number of jobs to submit that do exactly the same thing, a job array is a way to go, but sometimes it's not possible and you want to script the submission. So you want to write a small script or a one-liner command in Bash that will run the sbatch command for you. You can do that thanks to the wrap option of sbatch. So if you have a submission script like this, you can put this option into the submission line, and then the contents of the script, so the part where you define your job steps, you can put it in a single string and use the --wrap option, and this will create a wrapper that pretends that you have created a submission script, but actually the submission script is only one line. I will just interrupt a few seconds this part to go back to the GPUs. So there's a question, what is the MPS generic resources and what is its use? Actually, the MPS is a CUDA technology that allows sharing GPUs among jobs. So it's not completely, entirely, properly integrated into Slurm, but actually the way it is defined here, you can request a portion of a GPU. So if you know that your GPU, your program is not able to use a full GPU, you can request half a GPU. So there will not be any enforcement of the fact that you request only half a GPU. So if you request half a GPU and you use all the memory, then the other job that might run will crash, or your job will crash. So it's not entirely built integrated, but it's a way to share a GPU among different jobs. Currently on Manback, it's only working for jobs from the same user. So you could be able, using that, to run two jobs with access to the same GPU and share the GPU. If your jobs are aware one of another and you program that correctly, you should be able to do that. And so the 100 which is there is a percentage. So if you request a GRS type MPS colon Tesla V100 colon 50, you are requesting half a GPU. If you put 25, you are requesting a quarter of a GPU. So again, this will just allow Slurm to schedule if you have 4 jobs that request a fourth of a GPU, they will all start at the same time on the same GPU, but Slurm will not be able to manage the allocation of the resources of the GPU itself among the different jobs. Okay, so back to the scripting of the submissions. So this is only if you have a few jobs, because if you have a large number of jobs, job arrays are always the way to go. So as I said, if you have a submission script, you can pack all your submission script into a single line and use it with a -- wrap. And so when you do that, you can use the tips that you have learned from the parallel computing session. So let's assume, for instance, that we have 3 files, data red, data blue, data green, in some directory. You can use ls to list them all, and then use xargs with sbatch with -- wrap, and here you put the resources that you need, and then myprog and the placeholder from xargs. So we've seen xargs in the parallel computing session. So this single line is equivalent to all those 3 lines, but you did not have to write them. Simply list the files in the directory, and xargs will start as many sbatch commands that are needed with this parameter, and this will be replaced by the output of this. And so here, if you have actually 5 or 10 files, it will start 5 or 10 jobs, and you would not have to start them all one by one. So you can also use parallel. So if you remember from the parallel computing session, I talked about parallel. It's exactly the same, using parallel and then sbatch and then the parallel options. With this single line, I will not explain too much. You can have a look at the slides of that parallel computing session to understand, but this single line is equivalent to all these lines with all the pairwise possibilities, 1A, 1B, 1C, 2A, 2B, 2C, and so on. So beware that if you do that, you can end up submitting a very large amount of jobs, and the more jobs you submit, the more job the scheduler has to do to schedule all the jobs. So if you have a large number of jobs to submit and those jobs are very short in time, it's a good idea to pack them into a single job. For instance, if your job is only 1 or 2 minutes, Slurm will spend more time scheduling the job than actually running the job. So assume that you have a program that needs to run for 1 minute, let's say, but you have to run it with arguments from 1 to 100. So what you do to pack them all in the same job is to use the -n1 -- exclusive option of srun. So this is a simple for loop in bash. And so here I say I request 8 CPUs, 8 tasks actually. And then for I going from 1 to 1000, I run srun with only one task, even though I asked 10, and then dash exclusive. And the dash exclusive here has a completely different meaning as the dash exclusive when used to submit a job. So it has nothing to do with the fact that you want your job to be alone on the node. It has to do with the fact that actually you are splitting the 8 tasks here into one task sruns. And so you have your program here, and then the ampersand here to actually start srun in the background. And so this will start 1,000 instances of srun, but with this constraint and this option, only 8 of them will be running at the same time. And as soon as one of the 8 currently running sruns has finished, another one starts. So it's a way to do micro scheduling inside the submission script. You submit a single job with 8 tasks, for instance, and then you run as many srun and so as many steps as you need. You put them in the background with the bash constructs ampersand. If you don't remember how it works, you can go back to the Linux session. And then one important thing is to use the wait command here to tell bash to wait until all the srun have finished. Otherwise, as you have put all the srun in the background, at this point, bash will say, okay, job is done, and the bash script will stop, actually, and the Slurm will consider that the job has finished. So you need to have the wait here. So again, this is a way to pack multiple small job into a larger job of decent size. Just like you can use parallel to submit multiple jobs, you can use parallel inside your submission script to do micro scheduling, just like you can use xargs. So the examples that you've seen earlier with xargs and parallel outside of the submission script, you can use the same type of constructs inside the submission script. So here, for instance, the loop here can be written in one line like this with the parallel option. So here, the dash capital P has to match the 8 here. You could use here the Slurm environment variable, Slurm tasks, to avoid having to write again the same figure. But here I just wrote it, otherwise my line would be too long for the slide. And then srun dash exclusive dash n9, your program and this parallel construct to run the same thing over 1 to 1,000. And again, you can use xargs inside your submission script with this micro allocation to start 8 by 8 instances of the my program on everything that is outputted by the LS data. Okay. One thing you can do is answer questions. So one question is, why using parallel or packing jobs versus defining a job array? So if you are able to do it simply with a job array, it's always a nice thing to have. Sometimes the way the information needs to be organized is more difficult to do, and sometimes you just have a few jobs, but it's, well, I mean a few less than 100, but you do not want to run them one by one. And for instance, I showed an example with a parallel here where I have actually 2 parameters, 1 and 2, one going from 1 to 3, the other going from A to C. You cannot do that directly with a job array. So the job array is only 1 parameter going from the beginning to the end. It's always an integer, but here, if I have a mix of integers and files, for instance, or even floating values, if you are doing parameter optimization by parameter sweeping, it's much easier to organize it with parallel than with a job array. Second question was, is there a limit of tasks allowed to be allocated to a single node? It's the number of CPUs on the node. If you have 32 CPUs on the node, you cannot allocate more than 32 tasks on the same node. There are ways to do that with dash over commit, but I do not recommend that, because you would then have more processes than you have CPUs, and there will be contention and context switching, and you don't want to do that if you don't know exactly what you're doing. So basically, the number of tasks allowed on a single node is the number of CPUs. And again, you can use the sinfo command to see how many CPUs are available on a node. But you don't need to care by default. If you specify a too large amount of CPUs for one node, Slurm will tell you when you submit that there's no configuration that allows that. So maybe I can test just to be sure. So if I want to run sbatch, and then I will use wrap name just to avoid writing, and then tasks. Yeah. Okay, so manback was not the right. We might have. Right there. Okay, actually we have nodes on manback with more than 100 CPUs per node, but here you see that if I request 200 tasks on the same node, Slurm tells me right away that there's no node configuration that will satisfy my request. Okay, so back to where I was. So I don't remember. Okay, that's the other point. If your jobs are too small, you need to pack them into one job. If your jobs are too large for the maximum load time, on every cluster, you will see that there's a maximum running time. I will show you on, for instance, limit 3. If you run sinfo, you see the time limit is 2 days. If I go to Dragon 2, for instance, the time limit, well, it's written there, it's 21 days in the long partition and 5 days in the batch partition. If your job needs to run for more than 5 days, then you will need checkpointing, and checkpointing, you're lucky, is actually the topic of this afternoon session. So make sure to attend the session this afternoon by Olivier if you have very long jobs, and you will see how to actually wrap jobs so that they can be stopped and restarted from the same point and resumed from the same point. So a bit of summary now. What you need to remember is that to choose the number of processes, you use --n tasks. To choose the number of threads, --CPUs per task. Oh, there's an S missing. So here you should have an S. It's CPUs per task. And then you use srun or MPI run depending on the version of MPI library that you are using. Most of the time now, srun will be used. And then you can set OMP num threads based on the Slurm environment variables. And then you can use variables that are set by Slurm, such as the task array ID or the task ID or proc ID, depending on which use case you are, to know actually which processor you are using. I didn't speak much about it except for the Slurm task array ID because it's the most important one. But actually, you must know that inside your MPI process or inside your OpenMP threads, you can request from Slurm the proc ID, which is the equivalent of the num thread, and the task ID, which is equivalent to the rank, so that you can actually organize the work based not only on the rank, but also on the CPU IDs that are associated to each rank. Okay, I hope this was a good way for you to start using Slurm. I want to mention also that there is a wizard that we set up, which you can find on the CC webpage, and it looks like this. So here you have a box where you can describe a job. Here you have a box where you can choose a cluster, and actually the clusters that are available depend on what you put here. And then here you have the script that is generated for you by filling in those values. So maybe I can show a live example. So I'm starting my browser and showing it to you. If I go to the CC website and I go here, the submission script generation wizard, I will increase the size, I will decrease it, okay. And so here I can put my email address, for instance, and you see that the right part is updated in real time. So my address is, I can put some name here, for instance, that job. The project is specific for Zenob. So those of you who have access to Zenob, you know exactly what your project is. But you see that if you specify a project, you can actually choose Zenob here. And this is a submission script that works for Zenob. It's not Slurm because Zenob is not running Slurm. It's running another software called PBS. But if I choose another cluster, a CC cluster, you see the sbatch Slurm command. So you see that depending on the cluster, the way to write the submission script can be a bit different. And we try to improve this wizard with the time. But for now, you can specify, for instance, also the output file. And you see that it comes here. I will just remove the project. And then you have to choose between the parallelization paradigms. So if it's embarrassingly parallel, so job array, you can choose here the number of arrays, and you see here the array goes from 1 to 3. And the idea is that you can copy paste this into your submission script, and then you can edit it if you want, because it's not possible to have all the options from Slurm inside this wizard. So the idea is that you can copy the script and paste it in a submission script on the cluster that you want to use. But this should get you started. And if it's an OpenMP, you see that CPUs per task is set. So if I increase number of threads here, you see that here number is increased as well. And here the OpenMP num threads is a variable is set up for you. Nice thing is that if I'm requesting a large number of threads on the same machine, you see that, for instance, here I'm at 24, and NIC4 and Dragon1 have been ruled out because those clusters do not offer computers with that amount of CPUs. So to have 24 threads, you cannot submit a job to Dragon2. And another, sorry, to Dragon1. But Dragon2, Hercules 2, and so on have machines with 24 CPUs, so it's working. The same here with MPI. If I click MPI, you can increase the number of processes, and you see that the number of the task here increases. And what you see is also that only clusters, well, Vega is dead now, but only clusters with a fast interconnect, so Omnipath or InfiniBand are offered when you use MPI. And then if you use MPI, you see also that you can choose the different types of distribution, all grouped on the same node. Well, there are no nodes with 10 times 24 CPUs, but if I go back here, okay, I have more options. And then I can leave no constraint, and you see that here we just have the strict minimum. There was a question about the file system, and you see here that you can choose global scratch or local scratch, and you have here a skeleton, a template to copy data from the home directory, for instance, or the global scratch to the local scratch, and then something like that. and then run your job and then copy back and remove your job. So this again will be explained by Ariel in a future session. And you get an estimation of the total number of CPUs. So 2 processes with 24 threads each is 48 CPUs, and total memory, which is 48 times this amount of megabytes, and the total amount of CPU hours. So this is a way to check that you did not request overhaul too much by comparison with what you actually need. So if you're not sure how to start writing your submission script, just go back to the CC webpage, click on the script generation wizard, and then fill in the form here, and you should have a submission script here that you can copy and paste in a submission file on your cluster of choice. And of course, if you choose here the method 3, this will be specific for the method 3. And for instance, you will see that the partition is batch and debug. So by default, it will submit to both partitions at the same time. And Slurm will start the job on the first partition that offers the resources, the earliest. And so if I choose another defunct Vega, for instance, the partition is called defq. And so here it's adapted based on the fact that you chose Vega rather than the method 3. And see if I choose NIC4, it's also defq, actually, because they are running the same cluster management software, but on Hercules it's called batch, on Dragon 1 diff, on Dragon 2 it's batch and long, and so on. So this is adapted based on the cluster. So this is all I wanted to talk to you about Slurm. So we still have time for questions. Do not hesitate to ask them in the Q&A. I will try to answer them the best I can. But for now, I think we can stop here. Thank you for your participation. Don't forget the surveys, and don't hesitate to ask questions in the Q&A.